Hello, and welcome back. Today, we're diving into the Sine Synth example from Cmajor in detail. Here's a data flow graph of what we'll be building. We'll start by taking MIDI notes, process their information, and feed them into a voice allocator. The voices will then be summed together to generate the output. Each voice, however, is made up of a network of processors like oscillators, ADSR envelopes, and more, which we'll explain in detail later. Let's get started. After downloading vscode and installing the Cmajor extension, open the command palette by pressing Ctrl, Shift, P and select Create a New Patch. Then choose Create New Patch without a GUI. I'll create a new folder to keep things organized and give it a name. This will create two files. The .cmajor patch file is a JSON file that defines key properties of a Cmajor patch, including version, unique ID, name, and optional details like description, manufacturer, and whether it's an instrument or effect. It also contains links to the files that belong to the project. The .cmajor file is where we write our code. It will generate a processor template using the project name. Let's try running the patch with the code block empty by selecting Cmajor, Run Patch. The Cmajor tab will open, displaying a console error stating that a processor must declare at least one output. Now let's switch to a graph. But we'll get the same error. Processors and graphs can only communicate with the outside world via their endpoints. This is the syntax. A synth needs a MIDI input and an audio output. Now that our patch compiles without errors, we can see the sections in the Cmajor tab. GUI, Inputs, Outputs, Graph, where we can see squares representing our endpoints, audio device settings, and options to generate code like C++, WebAssembly, and others. Node. A node is a setup space. For a non-programmer, imagine you're in your music studio, setting up different pieces of equipment. Each piece of gear, like a synthesizer, effects unit, or mixer, needs to be connected to work together. In Cmajor, a node is like setting up one of those pieces of gear in your studio. For a programmer, it's similar to creating objects in code, where each node represents an instance of a specific component. Connections. Connections in Cmajor are like the cables in your studio. Just as you would connect different pieces of equipment with audio cables, in Cmajor, you connect different components of your sound processing chain using connections. Connections in Cmajor function similarly to how you might wire up function calls or object methods in a program. Voices. The voice essentially encapsulates all the necessary components to generate and modulate a single note of sound. It's also structured as a graph, where we'll connect various processors to shape the sound. Voices are triggered by events, which generate streams of audio. The main nodes we'll be using are note to frequency, envelope, and oscillator. When we compile, we'll encounter an error because note to frequency is not defined yet. Let's define it by specifying its note input event and float 32 output event. The processors aren't showing up in the graph section, and that's because we haven't instantiated them in the main graph yet. Let's fix that. Now, we can see our voice graph or subgraph with the nodes and their inputs and outputs clearly displayed. Since we need polyphony, we'll require multiple voices. We can simply declare an array of voices. Let's use 8 for this example. Although the array won't be visually represented in the graph, that's not an issue. Next, let's wire up the nodes using the arrow operator. The input event of the voice is connected to note to frequency, which then connects to the oscillator input, accessed using the dot operator. The input event is also routed to the envelope input. To generate our output, we'll perform a multiplication. ADSR amplitude modulation shapes the dynamics of the sound by multiplying the ADSR envelope with the oscillator's audio samples. Now we can see our nodes successfully connected. Let's instantiate the nodes in the main graph. The number 8 represents the number of voices, and since we'll be using this for voice allocation, we can define a global variable called voice count to give it meaning. The standard library provides a processor called voice allocator, which checks for an inactive voice. If one is available, it assigns the new note to it. Otherwise, it steals the least recently used active voice. Now, let's make the connections in the main graph. The MIDI input is connected to the MPE converter from the standard library, which converts MIDI messages into a stream of node event objects, such as node on, node off, pitch bend, slide, pressure, and control, that are then fed into the voice allocator. The allocator's output is connected to feed the voices. The voices are then summed together and routed to the output. This completes the global graph, showing all the connections. In the next video, we'll add velocity sensitivity and implement an ADSR processor using Faust. Then wrap it all up by generating a VST plugin that you can use in a DAW. Make sure to like and subscribe.